All right, let's dive right in. We're going to be looking at something really interesting today. In probability theory, we often want to compare different processes, right?
Yeah.
Like, is one bigger than another? But sometimes it gets kind of messy.
Yeah, definitely. And especially in those really complex systems where it's not obvious.
Exactly. So that's where this idea of germ order comes in.
Right. And it gives us like a non-standard way to look at things.
Okay, so what is this germ order?
So it's all about how we compare stochastic processes. And today we're going to focus on two main types: branching random walks.
BRWs.
Yeah, exactly, BRWs, and also on these rumor processes. And the way we do this comparison is through their probability generating functions.
Okay.
But here's the catch. We're only going to be looking at what happens near $Rs.
Okay, so I know generating functions encode a lot of information about a random variable.
Okay,
all right?
exactly.
But what's so special about $Rs?
Well, near C100, that's where things get really interesting, because the behavior of the generating function in that region, it tells us a lot about the tail probabilities.
Tail probabilities. Right?
Yeah, and that's all about those extreme events, the stuff that happens far away from the average.
Right. The unlikely but impactful events.
Exactly. And for processes like BRWs or rumor spreading, those tails, they basically control whether things die out or survive. So by looking at generating functions near CAU$1, we can compare processes even when it's impossible to directly compare them step by step.
So what you're saying is that germ order can tell us something fundamental about whether a process is going to vanish or persist, even if we can't, like, trace every little detail of how it evolves compared to another process.
Right. And what's really fascinating is germ order can sometimes tell you that one process will go extinct just because another one does, even if there isn't like a direct causal link between them.
That's pretty mind-blowing. So we're talking about BRWs and rumor processes. Can you, like, just remind us quickly what those are and why this germ order thing is so useful for them?
Sure. So branching random walks, right? They involve these particles and they're moving around. It could be like, I don't know, physical space or even different types of individuals.
Right.
And these particles reproduce. And the number of offspring they have and where they end up can get really complicated.
Okay, and rumor processes.
So think about information spreading. It could be on a network, a population, anything. We're going to be focusing on these firework models.
Firework models.
Yeah, firework and reverse firework models. They're on graphs, and it all depends on like how many sources there are and how far their influence spreads.
Okay, so with BRWs, you're saying germ order can tell us something about the survival of a population, maybe in a constantly changing environment.
Exactly.
And for rumors, it's like, will the information spread widely or just fizzle out?
That's it, yeah. And what makes germ order really useful is that it can handle situations where the rules of the game are different depending on where you are, what time it is, all sorts of stuff.
These inhomogeneous cases.
Yeah, inhomogeneous. Those are the ones that are really hard to study with like the usual methods.
Right. So our listeners, they're all pretty familiar with probability theory.
Yeah.
But we are going pretty deep here. We're diving into a research paper that is like really pushing the boundaries of what we know about germ order.
Oh, for sure.
So buckle up, everybody. Let's start with the absolute basics. What exactly is germ order, like mathematically?
Okay, so let's contrast it with something more familiar.
Like what?
Classical stochastic order.
Okay.
You've got two random variables, say $6 and right? 6 is stochastically larger than $ick. Well, if it tends to take on larger values.
Okay.
Like for any number of dollars, the probability that $6 is bigger than dollars is at least as big as the probability that dollars is bigger than dollars.
Okay, so it's like a direct comparison of their distributions.
Yeah, you got it. Now, germ order, it's a different beast.
Okay, how so?
So we're dealing with probability measures, right? Let's say Umalu. Germ order, written numaludunu, it's all about comparing their generating functions.
Okay, remember, generating functions, those are like the DNA of a probability distribution.
Yeah, exactly. Now, let's call the generating functions UMO A, UMLN. And let's say ZUMLIS is a vector where every component is between 0 and 1.
Right.
We say MUUZ is germ larger than UN if DUML is less than or equal to 0, but here's the crucial part.
There's always a crucial part.
This inequality only has to hold when ZIMLIS is really, really close to the vector of all ones.
So not for all Zillis.
No, just in this tiny region.
Like a neighborhood around 0, 1.
That's it.
So what if the inequality holds everywhere? For all Zillers?
Then you have a stronger condition. That's called probability generating function order, or PGF order for short.
PGF order.
Yeah, so if you have PGF order, you automatically have Germ order.
Right, because if it holds everywhere, it definitely holds in that little neighborhood near 1.
Exactly. But you can have germ order without PGF order.
Interesting. So germ order, it's kind of like a weaker but more flexible way to compare these distributions.
Yeah, you could say that.
Okay, but is it even like mathematically sensible? Does it follow the usual rules of ordering?
It does. It does. Germ order is a partial order.
Partial order.
Yeah, so it's reflexive. Any measure is germ larger than itself. It's transitive. If one is germ larger than a nu and no is germ larger than nu, then the mu is germ larger than delta 1.
Makes sense.
And it's antisymmetric. If no is germ larger than mu and nu is germ larger than a mu, then they have to be the same measure.
Okay, but why only partial? Why not a total order?
Well, you might have two measures where neither one is germ larger than the other. Their generating functions might cross in that crucial neighborhood near 1.
Okay, that makes sense.
Right.
So when we talk about germ order, we can do it for individual measures or for whole families of them, right?
Yeah, that's right. Like if we're talking about branching random walks, we might have a different offspring distribution at each location.
Right.
So you have a family of measures indexed by the locations.
Okay.
Now, one family is germ larger than another if each individual measure in the first family is germ larger than the corresponding one in the second family. But, and this is important,
Another crucial part.
that little neighborhood near 1 where the inequality has to hold, it has to be the same for all the measures in the families. We need that consistency across the whole family.
Okay, so we're starting to see how this abstract idea of comparing generating functions near 1 can be used to relate the behavior of different BRWs or maybe rumor spreading processes.
That's right.
But before we get too deep into that, let's zoom in on a specific aspect. When we talk about these processes, we often care about the total number of offspring a particle has, or the total number of people who hear a rumor, right?
Definitely.
How does germ order play with that?
So if we think about BRWs, we've got this multidimensional generating function, a genomore, right? It tells us about the number of offspring of each type.
Right.
But we can simplify that and just look at the total number of offspring regardless of their type.
Makes sense.
That gives us a one-dimensional generating function.
Okay.
And what Theorem 3.1 tells us is that if germ larger than AD dolars in terms of the full multidimensional generating functions, then the same relationship holds for the simplified ones that just track the total number of offspring.
So germ order in the full detailed process implies germ order in the simplified one.
Right.
Does it go the other way around?
Sometimes. But there are some important conditions. If both processes are independently diffusing, meaning the offspring just spread out randomly without any coordination,
Right.
and if they have the same dispersal mechanism, then germ order in the total offspring count actually implies germ order for the full processes.
Okay, so in those simpler cases, we can just focus on the total counts.
Yeah. But the paper makes it very clear. If things are more complicated, if the processes aren't independently diffusing, or if the dispersal mechanism is different, then just looking at the total count isn't enough.
Right. So while that total offspring count is useful, it doesn't always give us the full picture.
Exactly. We need to be careful.
All right, so let's assume we're in this simpler case of independently diffusing processes with the same dispersal mechanism. We want to figure out if one process is germ larger than another. How do we actually do that in practice?
Well, Theorem 3.2 gives us some tools. It looks at the moments of those total offspring distributions.
Moments as in like the mean, the variance, and so on.
Exactly. So let's call the total offspring random variables u and y. The first part of Theorem 3.2 says if you find a moment, like the third moment or the fifth, where u has a bigger moment than yy, then you can find a small enough region near 0.
Near 0, not 1.
Yeah, near 0 in this case. And in that region, a certain inequality involving exponential functions of those random variables will hold.
Okay, so a difference in moments can give us this inequality with exponentials. Interesting. What about the second part of the theorem?
The second part says, okay, what if the first few moments are the same?
Like the mean and variance are equal.
Yeah. Then it gives us another condition based on the next moment, but again with these exponentials. And this time, it has to hold in a small region near 1.
Back to 1.
Yeah. And critically, that region has to be the same for all locations here.
Right, that consistency across the whole family of measures.
Exactly.
These conditions seem pretty specific.
They are, but that's what makes them useful. They give us something concrete to check.
And Theorem 3.3, that's another tool, right?
It is, yeah. It uses factorial moments instead of regular moments.
Factorial moments, those are like the expected value of 6 piers times 6 minus 1 times 6 minus 2, and so on.
Right. They're often easier to work with, especially for certain kinds of distributions.
Okay.
And Theorem 3.3 gives us similar conditions to Theorem 3.2, but in terms of these factorial moments.
So we've got these different ways to try and establish germ order. Moments, factorial moments, all sorts of tools.
Yeah.
But then the paper dives into a specific type of distribution, mixed Poisson distributions.
Yeah, those are really interesting.
That makes them special.
Well, in a regular Poisson distribution, you've got a fixed rate parameter, right?
Right.
But in a mixed Poisson, that rate parameter is itself random.
Okay, so it's like a Poisson distribution with an extra layer of randomness.
Exactly.
How does germ order work with these mixed Poissons?
Proposition 3.5 gives us some conditions. It says if the expected value of the random rate parameter is bigger for one process than another, then you might have germ order, at least locally.
Locally?
Yeah, meaning it might only hold for specific locations.
Okay.
But then it gives another condition for the whole family of measures. It says if a certain inequality involving exponentials of the random rates holds in a small region near 1, the same region for all dollars.
There it is again, that consistency.
Yeah, then you have germ order for the whole family.
The paper also mentions that even if one process has a higher probability of having 0 offspring than another, it can still be germ larger.
Right.
That's counterintuitive.
Yeah, it highlights that germ order is really focused on what happens in C(eta)(1) near those extinction probabilities.
Not about the whole distribution.
Exactly.
And then there were some examples, right?
Yeah, examples 3.6 and 3.7, they really drive this point home.
How so?
They compare a regular Poisson distribution to a mixed Poisson, where the rate can take on 2 values, one above and one below the mean of the regular Poisson.
Okay.
And depending on the probabilities of those 2 rates, you can get germ order going either way.
So even though both distributions have the same mean, their behavior near 1, which is what germ order cares about, can be drastically different. Okay, so we've been talking a lot about these total offspring distributions, but the paper also goes into the spatial aspect of branching random walks. It compares independent diffusion, where offspring just spread out randomly, to non-independent diffusion, where there might be some correlation in how they move.
Right.
Does one type of diffusion always lead to a germ larger process?
Nope.
Nope. The paper gives us 2 examples.
Okay.
Example 3.8 shows that if all the offspring from a single parent end up being of the same type clustered together,
Okay.
that can actually result in a germ smaller process compared to independent diffusion.
So spreading things out can be beneficial.
Yeah, in this case it seems to be.
But then example 3.9 shows the opposite can happen.
Right. It constructs this non-independent diffusion where the offspring are deliberately spread out more evenly.
Okay.
And that can actually result in a germ larger process.
Oh, wow.
So the way things are dispersed, the strategy, not just the total number, can really matter. So the paper is saying that both independent and non-independent diffusion have their advantages and disadvantages.
Yeah. It depends on the specifics of the process.
And germ order allows us to analyze that.
Exactly.
All right, we've laid a lot of groundwork here. We've talked about what germ order is, how it relates to moments and factorial moments, and how it applies to different kinds of diffusion.
Right.
Now, the big question, how does all of this help us understand the long-term behavior of these processes? Like, will they survive or go extinct?
So let's talk about survival and extinction in a branching random walk.
Okay.
We say the process survives in a region if it never completely dies out in that region.
Makes sense.
And we're interested in the extinction probability,
Right.
$1.
Which is?
The probability that the process will go extinct in the region, $1, starting from a single particle at location $6.
Okay.
Now, Theorem 4.4 is where the magic happens.
Hit me with it.
It says if you have 2 branching random walks and one is germ larger than the other, then if the smaller one survives in a region, the larger one will too.
So germ order gives us a way to deduce survival properties of a process by comparing it to another process that we understand better.
Exactly. But, and this is a big but,
Always a but.
germ order doesn't necessarily tell us about extinction probabilities. It just tells us about survival. Like the germ larger process, it might actually have a higher probability of going extinct overall, even though it's guaranteed to survive if the smaller one does.
That's weird.
Yeah, it's a subtle point. But if you have the stronger condition, PGF order, then you do get a direct comparison of extinction probabilities.
Okay, so germ order is really about the boundary between survival and extinction.
Yeah, that's a good way to think about it.
Now, you mentioned earlier these FBRWs, these branching random walks with a finite type property.
Right.
How do they fit into all of this?
So FBRWs, they're a special kind of branching random walk where you can essentially group all the different types of particles into a finite number of categories. And for these FBRWs, we have some pretty good tools for figuring out when they survive. It all comes down to the properties of a certain matrix.
A matrix?
Yeah, the mean matrix. It tells you the average number of offspring of each type that a parent particle produces.
Okay.
And remark 4.5 in the paper tells us that if you have a BRW and you can compare its offspring distributions to those of a surviving FBRW, and those distributions are germ larger in a certain sense, then your BRW will also survive.
So we can leverage what we know about FBRWs to understand more complex BRWs.
That's the idea.
And the paper gives us some examples of that.
Yeah, examples 4.6 and 4.7. They look at BRWs with mixed Poisson offspring distributions and compare them to FBRWs with regular Poisson distributions.
Okay.
And using germ order, they show that even if those mixed Poissons sometimes have rates below the critical threshold for survival, the overall process can still survive if it's germ larger than a known surviving FBRW.
So again, germ order allows us to go beyond simple averages and look at the interplay between different parts of the process. Okay, so we've covered BRWs in a lot of detail.
Yeah.
But the paper doesn't stop there.
It goes on to look at branching processes in varying environments. BPVEs.
BPVs, okay.
What are those?
They're kind of like branching random walks, but instead of moving through space, they move through time.
Okay.
And the key thing is that the offspring distribution can change at each time step.
So the environment is dynamic.
Right.
That seems like it would make things even harder to analyze.
Oh, it definitely does. And what's really interesting is that survival in a BPVE, it's not just about whether the average number of offspring is greater than 1 or less than 1.
Like it is in a regular branching process.
Right. With BPVEs, you can have survival even if the average number of offspring is always less than 1.
That's counterintuitive.
Yeah, it is. But if you manage those fluctuations in the number of offspring just right, you can get survival.
Okay, so how does germ order come into play here? Proposition 5.1 tells us that if we can find two BPVEs, and the generating functions of one are consistently germ smaller than the generating functions of the other, and the second BPVE survives, then the first one will too.
So germ order lets us compare these BPVEs even when the environment is changing.
That's right. And there's a lemma that helps us actually work with those generating functions. Lemma 5.2.
What does that do?
It relates the inequality between generating functions to an inequality involving the tail probabilities of the offspring distributions.
Okay, so it gives us a more concrete way to check if germ order holds.
Yeah.
And there's an example, right?
Yeah. Example 5.3. It looks at a very simple BPVE where each particle can have either 0 or 1 offspring.
Okay.
And it shows that this BPVE can survive even if the probability of having 1 offspring is always less than or equal to 1/2.
So even with low average offspring numbers, you can still get survival.
Exactly. As long as those probabilities of having 0 offspring don't add up too quickly over time.
And then there's proposition 5.5, which gives us a more general condition for survival.
Right. It uses this binary offspring example as a benchmark and gives us conditions based on the probabilities of having different numbers of offspring.
Okay.
And then finally, theorem 5.6. This is a big one.
Lay it on me.
It shows how germ order can be used to study BTVEs where the moments of the offspring distributions might not even exist.
What does that mean? Moments might not exist.
It means the distributions might be so spread out that things like the mean or the variance are infinite.
Okay, so these are really wild processes.
Yeah, they are. But theorem 5.6 says if you can find another BPVE that has finite second moments and the generating functions of your BPVE are germ smaller than those of the other one and the other BPVE survives, then yours will too.
So germ order allows us to bridge the gap between those well-behaved BPVEs and the crazy ones.
Exactly. It's a really powerful tool.
Okay, so we've covered BRWs, BPVEs.
Yeah.
The paper's almost done, right?
Almost. It finishes with rumor processes.
Those firework models you mentioned earlier.
Yeah, those. So we're imagining this linear network, right?
Okay.
And at each site, you've got these stations that can be of different types.
Different types.
Yeah, like different abilities to spread the rumor.
Okay.
And each station has a random radius. That's how far it can send the rumor.
Okay, I'm picturing it.
So in the firework process, one station starts spreading the rumor.
Like an initial spark.
Right. And then any stations within its radius pick it up and start spreading it too.
And so on.
Exactly. And in the reverse firework process, it's more about listening. A station gets informed if it's within the radius of an active station.
Okay, I see.
And just like with BRWs, we're interested in whether the rumor survives or dies out.
And we have the same distinction between annealed and quenched survival, right?
Yep. Annealed means averaged over all possible configurations of stations and radii, and quenched means conditioned on a specific configuration.
Got it.
Now, the paper talks about why having multiple types of stations is interesting.
Okay, why is it?
Well, if all the types have the same radius distribution, it's basically the same as having just one type.
Right. That makes sense.
But if the radius distributions are different, or if the way the stations are arranged is correlated across sites.
Not independent.
Yeah, non-independent. Then things get really interesting.
Okay, and the paper gives us some theorems about when these rumor processes survive or go extinct.
It does, yeah. Theorem 6.4 tells us about homogeneous firework processes, where everything is the same at every site.
Okay.
And it connects survival to the behavior of the generating function.
The generating function, always coming back to that.
It's a powerful tool.
And theorem 6.5, that's about reverse firework processes, right?
Yeah, homogeneous ones. It gives us a condition based on a certain sum involving the generating function and the radius distribution.
Yeah.
And then theorems 6.6 and 6.7 extend those results to heterogeneous cases where things can change from site to site.
So we've got all these conditions for survival and extinction. But then the paper goes back to germ order, right?
Yeah, in the final section, it shows how germ order can be used to compare two different rumor processes.
How does that work?
Well, you need some assumptions. Assumption 6.9 says the station configurations have to satisfy germ order. And there's also a condition on the radius distributions.
Basically, if one process has a station with a huge radius, the other one should have a decent chance of having a station with a pretty big radius too.
Yeah, something like that.
And assumption 6.82, that's similar but with PGF order.
Right.
And then theorems 6.11 and 6.12 tell us what we can conclude about survival and extinction based on those assumptions.
Right. Like if one rumor process survives and the other one has station configurations that are germ larger, then the second process will also survive.
So again, germ order helps us leverage knowledge about one process to understand another.
That's it.
And the paper finishes with some examples, right?
Yeah, some really cool examples. They show how rumor processes can sometimes behave in really surprising ways.
Yeah, give me one.
Example 6.13 shows that a firework process can survive even if there are long stretches where the average number of stations that can spread the rumor is less than one. So even if things look bad for a while, you can still get survival if there are occasional bursts of activity.
That's pretty amazing.
And example 6.14 shows that having a mix of different types of stations can be crucial for survival.
Even if some of those types are individually unlikely to spread the rumor very far.
Exactly. Diversity matters.
Wow, so we've gone through a lot.
We have.
We started with this abstract idea of germ order, comparing generating functions near one.
Right.
And we saw how it can be used to analyze the survival and extinction of branching random walks, branching processes in varying environments, and even rumor processes.
Germ order, it's a powerful tool for understanding complex systems.
It really is, and I think it's amazing how it can reveal these subtle connections between processes that might seem very different on the surface.
I agree.
So, for those of you listening who want to dig even deeper into the math, all the details and proofs are in the paper, of course.
Definitely worth checking out.
And with that, I think we've reached the end of our deep dive.
Thanks for joining us.
Until next time.
All right, welcome back to the deep dive. So today we're going to be looking at a really interesting area, and it kind of has to do with, when we compare random processes, right? And we're going to be looking at things like branching random walks, how rumors spread, that kind of thing. And usually when we compare random processes, we think about, is one bigger than the other?
Right.
Is one always sort of doing more than the other? And that's like the classical way to think about it. But what if we can't really compare them that directly? What if one isn't always bigger than the other?
Yeah.
So there's this other idea, it's called germ order. And it gives us kind of like a different perspective, a different lens through which to view these systems.
Yeah, germ order, it provides a different way to look at the problem. So I guess maybe the standard way of comparing these processes is like a pathwise comparison.
Right.
Where you're looking at, is one always bigger than the other?
Yeah.
Germ order kind of shifts the attention away from the particles themselves to the generating function.
Right.
And so the generating function is just a way of encoding all the information about the probabilities of different outcomes of the process into a single function.
Oh, what?
And then germ order essentially says one process is greater than another one in this germ sense if its generating function is smaller, but near a particular point, near one.
Oh, okay. So it's not just smaller overall. It has to be
smaller near
one.
Yeah.
All right. So what do we mean by near one? Like, so if we're looking at a rumor spreading, right? Maybe one rumor spreads faster at the beginning, but then another rumor later on, after it's already spread to a lot of people, it kind of has more staying power.
Yeah, that's right. So you can think of it as like
is that what
germ order is?
Is that what it's getting at?
Yeah. Germ order is concerned about the tail behavior of the process.
Okay.
So you're looking at like, okay, if the rumor is already spread to a lot of people, what's the chance it continues to spread?
Right. Okay.
So that's one way to think about it.
So it's not necessarily which one always spreads faster, but which one has a lower probability of just dying out when it's already pretty prevalent.
Yeah, and that corresponds to the argument of the generating function being close to 1.
Okay.
When the argument of the generating function is close to 1, you're looking at the probabilities of large outcomes.
Right. Okay.
So in the branching process, that's a large number of offspring. In the rumor spreading, that's a wide spread of the rumor.
Right.
So if the generating function of one process is below another one near 1, that suggests that the probabilities of these large events are smaller for that process.
Right. So it's not about which one always has a bigger impact, but which one has a lower probability of fizzling out when it's
exactly.
Yeah, I agree.
Yeah. And this could be useful because there might be processes where one starts faster than another.
Right.
But then in the long run, it dies out more quickly.
Oh, interesting. Okay.
So germ order allows you to compare those two processes.
Okay. Now, the research that we're looking at today, it takes this idea of germ order and it extends it to processes that are described by multidimensional generating functions. And we talked about generating functions before, but it was more one-dimensional, like the total number of offspring. What do we mean by multidimensional now? And what does that allow us to look at that maybe we couldn't before?
Right. So multidimensional generating functions allow us to analyze much more general scenarios. So for example, if you're thinking about a branching random walk where each particle can produce offspring, not only of different numbers, but also of different types.
Oh, right. Okay.
At different locations in space.
Yeah.
And in that case, you can't really capture all that information using a single one-dimensional generating function. You need a higher dimensional generating function to keep track of all that.
Right. So instead of just looking at the total number of offspring, we're keeping track of, the number of each type of offspring, where they are.
Exactly.
And all of that.
So that's
at the same time.
Yeah. So it allows you to compare processes with much richer structure.
Right. Okay.
And not only that, it also allows you to compare processes where the offspring events are not necessarily independent.
Okay.
So, if the number of offspring that one particle produces depends on the number of offspring that another particle produced,
right,
you can use a multidimensional generating function to account for that.
Okay. So it's way more powerful.
Right. Yeah.
And in the paper, they talk about how this is especially useful when we're looking at inhomogeneous environments. What makes inhomogeneous environments so hard to work with? And how does germ order offer a way to kind of get around some of those challenges?
Right. So inhomogeneous environments are basically environments that are not uniform.
Right.
So, maybe the rules governing the branching process are different depending on where you are in the environment.
Okay.
And this can make things a lot harder to analyze.
Yeah, I can imagine. Okay.
Because, you can't just use the same techniques that you would use for a homogeneous environment.
Right.
So, for example, in a homogeneous branching random walk, if the expected number of offspring is greater than 1, then we know that the process will survive.
Okay.
It will grow exponentially.
Right.
But in an inhomogeneous environment, that's not necessarily true.
Oh, interesting. Okay.
So, even if the average number of offspring at each site is high,
Okay.
the process could still die out.
Oh, wow. Okay.
If there are certain regions of the environment that are unfavorable to survival.
Right. So it's like a couple of bad spots can totally mess up the whole
That's right.
process.
That's right.
Okay.
And Germ Order provides a way to address this by comparing the process whose behavior you don't fully understand in the inhomogeneous environment to a simpler process.
Okay.
Maybe a process in a homogeneous environment.
Right.
Where you do understand the behavior. And if you can establish a relationship between these two processes using Germ Order,
Okay.
then you can use that to infer something about the behavior of the more complicated process.
Okay. So you're essentially comparing it against a simpler process that we already know how it behaves.
That's right.
Okay.
Yeah.
That's cool. Now, they also mentioned in the intro this idea of PGF order, right? And we talked about Germ Order, which is, kind of like near one.
Right.
How does that relate to PGF order? And what's kind of like the main difference between the two?
Right. So PGF order stands for probability generating function order.
Okay.
And it's a stronger condition than Germ Order.
Okay.
So we say that one process is PGF greater than another process if the generating function of the first process is less than or equal to the generating function of the second process for all values of the argument between 0 and 1.
So for the entire range?
For the entire range.
Okay.
Germ Order only requires that this inequality hold near 1. So if you have PGF order, then you automatically have Germ Order.
Okay.
But you can have Germ Order without having PGF order.
Right.
And Germ Order is...
so if they're PGF ordered, then they're automatically Germ ordered, but not the other way around.
Not necessarily the other way around.
Okay.
Yeah.
Cool. And finally, the intro mentions that they're going to talk about a few specific types of processes. We have branching processes in varying environments, BPVEs. Yeah. And then they also mention rumor processes on graphs and some special cases called firework and reverse firework processes.
Right.
Are they going to be like actually simulating these things or?
Okay. They're going to be focusing more on the mathematical theory behind these processes.
Yeah.
So they're going to be looking at the generating functions. They're going to be looking at how to prove certain properties of these processes using Germ Order.
Right. Okay. So it's going to be a pretty math-heavy deep dive.
Yeah, a little bit more on the theoretical side.
Okay, cool. All right, so let's jump into the first section here, Germ Order, a deeper look. And they start by talking about generating functions, specifically this general multidimensional generating function, G mu of Z given Y. What is this function really telling us? And let's kind of break down exactly what it means mathematically.
Right. So this functions as a way of encoding all the information about the probabilities of different outcomes of a branching process at a particular site Y into a single function.
Okay.
So the input to the function is a vector Z, which has one component for each type of offspring.
Okay.
And the output of the function is a number between 0 and 1.
Right.
Which represents the expected value of a certain quantity that depends on the number of offspring of each type that are produced at that site.
All right. So we have like this vector Z, right? And it's got all these components, one for each type of offspring. And the components are between 0 and 1. What do those components represent?
Right. So the components of Z represent discount factors.
Okay.
So for each type of offspring, you have a discount factor between 0 and 1.
Okay.
And the closer the discount factor is to 1, the more valuable that type of offspring is.
Right. Okay.
So if you have a discount factor of 1, that means that that type of offspring is just as valuable as the parent.
Okay.
If you have a discount factor of 0, that means that that type of offspring is worthless.
Right. So it's kind of like saying, we care more about certain types of offspring than others, and we're encoding that in these different Z values.
That's right.
Okay. So then once we have those Z values, what does the generating function actually calculate? Like, how does it use those Z values?
Right. So the generating function calculates the expected value of the product of the discount factors raised to the power of the number of offspring of each type.
Okay, so let me just repeat that back. So we're taking the discount factors for each type, raising them to the power of how many of that type we have, and then we're multiplying all those together. And the generating function is giving us the expected value of that whole.
That's right, yeah.
Okay. And that expected value is going to be between 0 and 1, right?
It's always between 0 and 1.
That's it, cool. Now, in addition to this multi-dimensional generating function, they also define a one-dimensional version. It's called phi y of t. It's equal to g mu of t times the vector of all ones given y. And that also equals the sum over all the different offspring configurations of mu of f times t to the power of the absolute value of f. What's going on here? We had all these different types before in the multidimensional version, but now we've collapsed it down to just this single variable t. What's the point of that?
Right. So this one-dimensional generating function is just the generating function of the total number of offspring at site y.
Okay.
Regardless of their type. So it's basically the same as the multi-dimensional generating function.
Okay.
Except that you're setting all the discount factors equal to t.
Okay. So instead of having these different z values, we're just using t for everything.
Right. Yeah.
So we're just focusing on the total count, right?
Right.
Okay. And then they say that, this mu, this family of measures, is uniquely determined by its generating function, yi. What do we mean by uniquely determined? And why is that such an important property when we're comparing things using these generating functions?
Right. So uniquely determined means that if you know the generating function,
Okay.
then you know the family of measures.
Okay.
And this is important because it means that if you can compare the generating functions of two processes,
Okay.
then you can compare the processes themselves.
Oh, okay.
So if you can show that the generating function of one process is smaller than the generating function of another process,
Okay.
then you know that the first process is in some sense smaller than the second process.
Right. So the generating function really captures everything we need to know about the behavior of the process.
That's right.
Okay. So that comparison is meaningful. It's not just like some abstract mathematical thing. It actually tells us something about the real underlying process.
That's right.
Okay. And then they list some properties of this GMU. So they say that it's continuous with respect to pointwise convergence of Z, okay? And that it's non-decreasing in each component of Z. What does that mean?
Right. So continuous with respect to pointwise convergence of Z means that if you have a sequence of vectors that converge pointwise to Z, then the corresponding sequence of generating function values will also converge to the generating function value at Z. And non-decreasing in each component of Z means that if you increase any component of Z, then the generating function value will not decrease.
Okay. So those seem pretty intuitive, but why is it important to actually state those as properties?
It's important to state these properties because they're used in some of the proofs later on.
Right. Okay. So we need those to be true.
Right. Yeah.
To actually make the rest of the math work.
That's right.
Okay. And then they talk about this construction of an independently diffusing family of measures, mu. That sounds like a specific kind of branching process or spread. What do we mean by independently diffusing here? How is that defined mathematically?
Right. So an independently diffusing family of measures is a family of measures where the offspring at each site are produced independently of each other.
Okay.
So you can think of it as each individual having its own offspring distribution.
Okay.
And the offspring distributions are independent.
Okay, so it's not like they're all influenced by some common factor. It's each one just doing its own thing.
That's right.
Yeah, okay.
And so the generating function in this case has a nice form.
Okay.
It's just a composition of the one-dimensional generating functions of the offspring distributions.
So we can actually write it in a more compact way.
That's right.
Okay. And they say that it's constructed based on a total offspring distribution, denoted by these rotor rays, and a stochastic matrix P. Can you unpack those two components for us?
Right. So the total offspring distribution, rho y, is the probability distribution of the total number of offspring that an individual at site y will produce.
Okay.
So, for example, if rho y of 2 is equal to 0.5, that means that an individual at site y has a 50% chance of producing 2 offspring.
Right. Okay. And so we have this total offspring distribution for each site.
That's right. Yeah.
Okay. What about this P matrix? What does that represent?
Right. So the stochastic matrix P represents the probabilities of an offspring moving from one site to another.
Okay.
So the ij entry of P
Okay.
is the probability that an offspring produced at site I will move to site j.
Okay. So it's like a transition matrix.
Right. It's a transition matrix.
Okay. And because it's stochastic, each row has to sum to 1.
Right. Yeah.
Because each offspring has to go somewhere.
Exactly.
Yeah. Okay, cool. All right, now that we have these definitions of, the generating function, independently diffusing families, let's move on to PGF order and germ order again. We talked about them conceptually before, but now let's get into the formal definitions and see what really makes them different mathematically.
Right. So PGF order is defined as follows.
Okay.
We say that a family of measures mu is PGF greater than another family of measures nu, if and only if the generating function of nu is less than or equal to the generating function of nu for all values of the argument between 0 and 1.
Okay, so it's pointwise, right? For every single value of z, the generating function for mu has to be less than or equal to the generating function for nu.
That's right.
Okay.
And the germ order is defined as follows.
Okay.
We say that a family of measures mu is germ greater than another family of measures nu if and only if there exists a delta between 0 and 1, such that the generating function of mu is less than or equal to the generating function of nu.
Okay.
For all values of the argument between delta and 1.
All right. So the key difference there is that PGF order is across that whole range from 0 to 1.
Right.
Germ order is just in this region near 1, right?
Yeah, that's right.
From some delta up to 1.
That's right.
Okay.
And so this delta might depend on the families of measures that you're comparing.
Right. Okay.
But it has to be the same delta for all the sites.
Oh, okay. So it can't be like a different delta at each site. It's got to be a global...
It has to be uniform delta.
Delta. Okay, cool. And then they mention that these orders, they hold for the whole families of measures if and only if they hold component-wise. What does that mean? Like, what do we mean by component-wise here?
Right. So component-wise means that you're looking at each site individually.
Okay.
So if you want to show that mu is PGF greater than nu, then you need to show the generating function of mu at site y is less than or equal to the generating function of nu at site y.
Okay.
For all sites y.
Right. Okay, so you've got to check it for every single site.
That's right. That's right.
Okay. And same thing for germ order.
Same thing for germ order.
Okay. So it's not enough to just show that it holds for like some average or something. You've got to actually check each individual site. Okay. All right. And then they say that that germ order is a partial order. What does that mean? Like, why is it a partial order and not like a total order?
Right. So a partial order is a relation that's reflexive, antisymmetric, and transitive.
Okay.
Reflexive means that every element is related to itself.
Okay.
And symmetric means that if two elements are related to each other, then they're the same element.
Okay.
And transitive means that if one element is related to a second element, and the second element is related to a third element, then the first element is related to the third element. Right. Okay.
So germ order satisfies all three of these properties.
Okay.
It's reflexive because the generating function of a family of measures is always less than or equal to itself.
Right.
It's antisymmetric because if the generating function of mu is less than or equal to the generating function of nu, and the generating function of nu is less than or equal to the generating function of mu, then the generating functions must be equal.
Right.
And if the generating functions are equal, then the families of measures must be equal.
Okay.
And it's transitive because if the generating function of mu is less than or equal to the generating function of nu.
Okay.
And the generating function of nu is less than or equal to the generating function of nu, then the generating function of mu is less than or equal to the generating function of 11.
Right. Okay. So it satisfies all the properties of a partial order.
Right.
And it's not a total order because we can't always compare two processes. Right.
That's right. Yeah. There might be two processes where neither one is germ greater than the other.
Yeah. You could have two generating functions that cross.
Right.
So one is bigger in one region and the other one is bigger in the other region.
Okay, that makes sense. All right, so now let's move on to theorem 3.1. And this theorem is about the relationship between germ order of the full families of measures, so using that multidimensional generating function G, and the germ order of just the total offspring distributions, using that one-dimensional generating function phi. So the first part of the theorem says that if G mu of Z is less than or equal to G nu of Z for Z in that germ region, so between delta and 1, then the phi mu of Z of T is less than or equal to phi nu of Z Y of T for T between delta and 1 for all Y. Can you walk us through why that implication holds?
Right. So the first part of the theorem is pretty straightforward.
Okay.
It's basically saying that if the multidimensional generating function of mu is less than or equal to the multidimensional generating function of nu, then the one-dimensional generating function of mu is less than or equal to the one-dimensional generating function of nu.
Okay.
And the reason for that is that the one-dimensional generating function is just a special case of the multidimensional generating function.
Right.
So if the multidimensional inequality holds,
okay,
then the one-dimensional inequality has to hold as well.
Okay, so it's kind of like saying if it's true for the more general case, then it has to be true for the specific case,
Yeah,
where we're just looking at the total number of offspring.
That's right.
Okay. Now, the theorem also has a converse part, but with an extra condition. So it says that if mu and nu are independently diffusing with the same stochastic matrix P, then if that inequality for the phi's holds, so phi mu of y of t less than or equal to phi nu of y of t, for t between delta and 1 and all y, then it follows that the inequality for the g's also holds in that same region. So how does this assumption of independent diffusion with the same p, how does that come into play? Why do we need that for this converse direction to work?
Right. So the assumption of independent diffusion with the same stochastic matrix P is needed because it allows us to relate the multidimensional generating function to the one-dimensional generating function.
Okay.
So if you have independent diffusion with the same stochastic matrix P, then the multidimensional generating function can be written as a composition of the one-dimensional generating function.
Okay.
And so if the one-dimensional inequality holds, then the multidimensional inequality has to hold as well.
Right. Okay. So the independent diffusion and the same P, that gives us this nice relationship between the multidimensional and one-dimensional generating functions.
Right. Yeah.
So if we know that the one-dimensional inequality holds and we have this nice relationship, then we can conclude that the multidimensional inequality also has to hold.
That's right.
Okay, cool. So essentially, in this specific case, we can just focus on comparing the one-dimensional generating functions, which are usually easier to work with. We don't have to deal with the whole multidimensional thing. That's exactly.
If we have this nice independent diffusion property.
That's right.
Okay.
Yeah.
But they also mentioned that, in general, just comparing the total offspring distributions at each site might not be enough to establish germ order between those full families of measures.
Yeah.
Like if we don't have this independent diffusion. So why is that? Why isn't it always enough?
Right. So if you don't have independent diffusion, then the offspring at different sites might be correlated.
Okay.
And so even if the total offspring distributions are the same at each site, the families of measures might still be different.
Right. Okay.
And so you might not be able to establish germ order.
Okay. So that correlation between sites, that can really mess things up.
Right. Okay. Now, we've kind of laid the groundwork here, but let's move on to the section 3.1, which talks about sufficient conditions for germ order for those independently diffusing families. So theorem 3.2, it focuses on comparing this 5IV to the minus t for mu and nu. We've been talking about Fiamati, so why are we suddenly introducing this exponential term here? How does looking at 5e to the minus t help us understand germ order, which is about t near 1?
Right. So the reason we're looking at 5IV to the minus t is because it's related to the moments of the offspring distribution. So if you take the derivative of 5e to the minus t and you evaluate it at t equals 0, then you get the nth moment of the offspring distribution. And so by comparing the moments of the offspring distributions, we can get information about the germ order of the families of measures.
Right. So we're using this exponential transformation to kind of access the moments, which then gives us information about germ order.
Right. Yeah. And this is a common technique in probability theory.
Right.
You know, whenever you want to relate the behavior of a generating function near 1 to the moments of the distribution, you can often use this exponential transformation.
And the paper mentions that the derivatives of the expectation of e to the minus 2 times z, evaluated at t equals 0, are directly related to the moments e of z to the k. Why is that? What's the connection there?
Right. So the reason for that is that if you take the derivative of e to the minus tz, you get minus e to the minus tz. And if you evaluate that at t equals 0, you get minus z.
Right.
And so if you take the expectation of that, you get minus the expectation of z.
Right.
Which is the first moment.
And if you take the second derivative of e to the minus tz,
Okay.
you get z squared e to the minus tz.
Right.
And if you evaluate that at t equals 0,
Okay.
you get z squared.
Okay.
And so if you take the expectation of that,
you get the expectation of z squared,
Right. Okay.
which is the second moment,
Okay.
and so on.
Right. Okay. So it's basically like every time you take the derivative, you're pulling down another factor of z.
That's right. Yeah.
And then the exponential term just goes to 1 when tit is 0.
That's right.
So you end up with the expectation of z to the
That's
k.
That's right.
Okay, cool. Now, the first part of Theorem 3.2, key. All right, welcome back to the deep dive. Today we're diving into something a little different, I'd say.
Yeah.
A really interesting way to compare these sort of evolving processes, you know, like branching random walks.
Yeah.
And also rumor processes, which kind of have some similarities when you think about it.
Oh,
This spreading out, right.
Right.
So branching random walks, kind of you can think of like a family tree, but not just a family tree, just growing, you know, like.
Just names on a page.
Yeah, names on a page, but it's spreading across locations.
Yeah, geographically, through different types, all sorts of things.
Exactly.
Yeah.
And rumor processes, you know, something starts and it spreads out through a population.
Right, exactly.
So we're looking at a specific way to compare them called germ order,
Mm.
which uses these pretty cool mathematical tools called generating functions.
That's right, yeah.
So what's the idea here?
So usually if we want to compare two random processes and see which one's, say, bigger in some sense, we might try and compare them directly, you know?
Yeah, head to head.
Yeah, like particle by particle, step by step.
Uh-huh.
But germ order offers a different perspective.
Okay.
It kind of looks at the probability of all the possible outcomes of these processes,
Okay.
all bundled up neatly in these generating functions.
Okay, so we're not comparing like the average outcome. We're comparing like every single possible outcome.
Yeah, it's like comparing their overall potential to thrive or persist.
Okay, so generating functions are like a way to see all the possibilities, kind of?
Exactly.
Okay.
Yeah, you capture the entire range of possibilities instead of just looking at what happens on average.
I got it.
Yeah.
And then this germ order is a way to compare those entire probability landscapes.
Precisely, yeah.
Okay, and I guess what makes this particularly useful is, you know, sometimes you can't do that direct comparison.
Right.
Yeah, it can be really complicated, you know,
Yeah.
even impossible in some cases to compare them directly step by step.
Right.
But germ order can still give us a way to compare them.
Got it.
So, for example, imagine you have two slightly different rumor processes, you know,
Okay.
spreading through a population.
Mm-hmm.
It might be hard to say for sure that one of them always has more people who've heard the rumor at any given time.
Yeah.
But their overall probability profiles, you know, as captured by these generating functions, might still be comparable
Okay.
using this idea of germ order.
Right. So even if you can't say at any given time, oh, this one's definitely bigger,
Right.
we can still look at the generating functions and say, oh, yeah, this one's bigger in this way.
Right. You can see which one is more likely to really take off
Okay.
or die out in the long run.
Got it.
Now, from what I understand, the original ideas around this germ order thing, they were for, you know, kind of simpler branching random walks where all the branches followed the same rules. But today we're really going into the complex stuff here.
Yeah.
What the source calls multidimensional generating functions.
Mm-hmm.
So why do we need this extra multidimensionality?
Well, because, you know, many real-world systems and the mathematical models that describe them are not uniform, right?
Right.
So if you think about that rumor spreading through a city, different neighborhoods are going to have different characteristics, you know.
Oh, for sure.
Like population density, social connections, how easily information travels.
Right.
And a single rule just won't capture that kind of complexity.
Got it.
So these multidimensional generating functions allow us to account for these variations.
Okay.
They can handle different types of offspring, so to speak, in a branching process, or different types of spreaders in a rumor process, each with their own potentially unique behavior.
Got it. So the multidimensionality is really just about adding that extra nuance to the model.
Exactly.
Okay.
Yeah, it makes it more realistic.
So our mission today is to really dig deep into this idea of germ order.
Okay.
In this more general multidimensional context.
Yeah.
So we need to understand exactly how it's defined, get comfortable with the notation, all the symbols and stuff, and see how it builds upon and differs from those more traditional ways of comparing random processes.
Exactly.
So it seems like we're really focusing on the fundamental mathematical tools here today.
Precisely.
Okay.
Yeah, it's about getting a solid grasp of the math
All right.
that allows us to make these comparisons.
So let's lay the groundwork.
Okay.
We got to understand these generating functions inside and out. How do we even represent these random processes using these mathematical objects?
Well, so at the heart of it, we're working with what are called families of measures.
Okay.
So imagine you have a set, we'll call it $.
Okay.
And this could represent different starting points for our process. Like different locations in a branching random walk, or different initial sets of informed individuals in a rumor process.
Okay.
And for each $, in this set $, we have a measure called $.
Okay.
And this measure is defined on a set denoted $7.
Okay.
Now, this as a set is a set of functions.
Okay.
Denoted by 5 elements from another set, accountable set $6 to the natural numbers, so 0, 1, 2, and so on. With the condition that the sum of all those in the set $, is finite.
Got it.
So that you can think of $6 as the different types of offspring, in the branching process, or the different ways the rumor can spread. So then Bali gives us the probability of seeing a specific configuration for $. Of these offspring types or spread patterns originating from Austin $.
Okay, so for each starting point, Mios gives us the probabilities of all the different possible outcomes. Okay. Where the outcome is a configuration called fallers. And fallers is like, it specifies the count for each type in.
Exactly.
Okay.
Yeah, so fallers tells you how many of type sectors are produced.
Got it.
Now, we can use this to define what's called the multidimensional generating function.
Okay.
Denoted by Ginny's.
All right.
And it's defined as the sum over all possible configurations, $5 in sex.
Okay.
And for each $, we take its probability and multiply it by a product.
Okay.
This product runs over all the elements, $6 and $, in sex.
Okay.
And for each sixers, we have a variable, we'll call it ZUCCA, which is a number between 0 and 1, raised to the power of B sexes, which is the number of type scales in the configuration.
Okay, so this sector is a vector, or each component is linked to a specific type in $6.
Exactly.
Okay, so what's the purpose of having these XLs in here?
Well, you can think of them as kind of tagging each outcome with a product of these Yekazol terms, where the exponent tells us how many of each type $6 occurred.
Okay.
So when we work with these generating functions, we can extract information about the probabilities of specific numbers of each type by looking at the coefficients of the resulting power series if we were to expand the function.
Got it.
It's a way to encode the entire probability distribution in a compact form that we can manipulate mathematically.
Got it. It's a way to be able to work with a potentially infinite number of outcomes.
Right, exactly.
Yeah. Okay.
Now the source also introduces this function phi-d.
Okay.
Which is defined as G math BF1.
So what is this telling us?
Okay, so here, math BF1 represents a vector where every component is 1.
Okay.
So math BF1 means we're setting Z equal to totters for all $6.
Okay.
Where 2 is a single value between 0 and 1.
Got it.
And if we substitute this into our definition of meal, we get fine equals the sum over all sums of fine times the product over all 6 all to the power of 2, which simplifies to the sum over all, times towers of the sum over all $6 of 2.
Okay.
Which is just the sum over all $6 of 25 the sum goes.
Where 5 is just...
Where 5 is the total number of offspring.
Okay.
Or the total amount of spread in the configuration.
Regardless of type.
Regardless of type.
Okay, exactly. So it's basically like a simpler generating function that just tracks the total number and not the types.
Exactly, yeah.
Okay, I got it.
So if we define hoi on as the probability that the total number of outcomes at hoi on toy, then phi dollar can be written as the sum from no equals 0 to infinity of toy on times 2 the dollar.
Okay.
And this is just the standard probability generating function for the total outcome distribution at DALI.
Got it.
And importantly, the expected total number of outcomes.
Yeah.
Which we can denote by E dollars, where 5 follows the distribution power.
Okay.
Can be found by taking the first derivative of respect to dollars and evaluating it at t equals 1.
Okay.
So E dollars equals phi ET.
So that connects this generating function back to, like, the more familiar expected value.
To familiar concepts like expected values.
Yeah.
Okay, that's good.
That's good. Now, the source also talks about independently devising families of measures.
Okay.
So these have a very specific structure.
Good.
They assume that the total number of outcomes at EA follows some distribution, which we can denote by phi, or equivalently tori.
Got it.
And then, given that there are no nodal outcomes, each of those outcomes independently chooses a type.
Okay.
$6 from $6, according to a stochastic matrix dollars.
Okay.
Now, this matrix is defined by its elements, tor effects, which is the probability that an outcome originating at I is of type 6. And the stochastic part just means that for any I, the sum of all $6 and $6 is equal to 1.
Okay, so it's a two-step process.
Right.
You first determine the total number of outcomes based on the starting point.
Yeah.
And then each of those outcomes independently decides on a type based on this matrix.
Right, exactly.
Okay.
And for such a family, the multidimensional generating function has a particularly elegant form.
Okay.
It's given by GZI equals phi, where it's equal to the sum over all $6 of 5.
Okay,
It's like a weighted average.
Of the values.
Yeah, it's a weighted average of the values where the weights are the transition probabilities from $6.
Right, and then we plug that into the one-dimensional generating function.
Exactly. We take that weighted average and plug it into the one-dimensional generating function, $6 of the total number of offspring.
Okay, that's pretty cool.
Yeah, it simplifies things quite a bit.
Yeah, so you've got the total outcome behavior, in fifth dollar, and then you've got the way those are distributed across types in the tuple. Okay, and the source mentioned branching, random walks, and rumor processes as examples of this. So how do these fit this independently diffusing mold?
Okay, so in a branching random walk, the Delhi sets 6 on dollars often represent the same thing.
Okay.
Like locations in space or different types of particles. So if the branching is independently diffusing, a particle at location 9 produces a random number of offspring, according to Boré, and each offspring then independently moves to a new location, $6, with probability Ty.
Got it.
For rumor processes, dollars might be the individuals in a network.
Okay.
And $6 could be different states of those individuals. For example, unaware, informed, spread the rumor, things like that.
Got it.
And independent diffusion in this case could mean that each informed individual independently contacts others and informs them with certain probabilities. What Yal is the informer and 6Y is the one being informed.
Okay, that makes sense.
Yeah.
So we've built up this foundation with these generating functions.
Right.
Now we can finally get to germ order itself.
Okay, so we have 2 types of order.
Okay.
Defined using these generating functions. The first is called PGF order.
Okay.
Short for probability generating function order. And we write it as more greater than or equal to the number with a subscript PGF.
Okay.
And we say that number is greater than or equal to number in PGF order. If their generating functions satisfy number is less than or equal to num for all possible values of Zellers in the range from 0 to 1.
So this PGF order is it's a kind of a strict requirement.
It is, yeah. It's a global comparison across the entire range of Zilla values.
Right, okay.
And this leads us to the concept of germ order, which is denoted by number greater than or equal to with a subscript term.
Okay.
And we say that number is greater than or equal to in germ order. If there exists some value, we'll call it dilate, between 0 and 1, such that the inequality jumper is less than or equal to holds for all Dilla in a restricted range. Specifically when all components of Zilla are between Dilla and lover.
Okay, so instead of needing the inequality to hold for all Stiller, it just needs to hold for Zilla versus S between a Diller and number? Exactly. Which is like, since ZBX is like this proxy for probability of, continuing, right.
Of success for type section.
Yeah.
Yeah.
This means that it's just focused on the probabilities that are really high.
Exactly. Yeah. Germ order focuses on those scenarios where those probabilities are high.
Okay.
And as you said, the term germ here alludes to the behavior of the process when it has a high chance of, growing or persisting.
Right. Okay.
Now, as the source notes, if dural wols is greater than or equal to a dural way in PGF order, then it automatically follows that duals is greater than or equal to a dural way in germ order.
Right, because you can just set delta to dollars, right?
Yeah, we can just choose delta equals 0. However, the reverse is not necessarily true.
Got it.
Two processes might be ordered in germ order, but not in PGF order.
Okay, so germ order is like a weaker condition.
It is, yeah.
It's more local.
It's a weaker, more local condition, yeah.
Now, the source also mentions that termu is greater than or equal to nuo in germ order, with a specific delta, hold in and only if nuo is greater than or equal to nuo in germ order, with the same delta for all in dollar.
Yeah.
And the same applies to PGF order.
That's right.
This seems like a pretty useful property because now we can just compare each starting condition independently.
Yeah, you can break down the overall comparison into a set of element-wise comparisons.
Exactly. Yeah.
And importantly, the source states that greater than or equal to, in the germ order sense, satisfies the properties of a partial order.
Okay.
So that means it's reflexive, transitive, and antisymmetric.
Okay, and that just means that this germ order is mathematically sound.
Exactly.
It's a well-behaved.
It's a well-defined relationship.
Yeah, relationship. Okay.
Yeah.
So we have these definitions now.
Right.
PGF order and germ order, and we understand the relationship between them.
Yeah.
And some of their key properties. So how does this germ order of these full multidimensional processes relate to those simpler one-dimensional total outcome distributions, spheres that we talked about?
Well, Theorem 3.1 in the source provides this crucial link.
Okay.
It states that if theorem fields is less than or equal to theorem for all vir in the range from delta to 1, which is the condition for a greater than or equal to Durmor mortar with parameter delta, then it must also be true that the corresponding total outcome generating functions satisfy is less than or equal to aeon of billion for all the range from delta to dollar and for all the aeon of dollars.
Okay, so if two processes are germ ordered, then their total outcome distributions are also germ ordered.
Exactly.
Okay. What about the other way around?
Okay, so the theorem tells us that the reverse direction holds if both Deller and Unir-Dellers are independently diffusing.
Okay.
And they share the same stochastic matrix Deller, which governs how the outcomes are distributed across types.
Yeah.
So in this specific scenario, if the germ order holds for the total outcome distributions with the same Deller for all Deller, then the germ order also holds for the full processes.
Okay. That makes sense.
Yeah, it simplifies things quite a bit.
Yeah, so if we know they're both independently diffusing, and they have the same pi-do matrix, then we can just look at those total number of outcomes.
Yeah, we can just focus on the total number of outcomes.
Yeah, okay.
And this becomes even simpler if the total outcome distributions don't depend on the starting point. Meaning that germ equals dermu and tornu equals dural for all dollar.
Got it.
So in such a homogeneous and independently diffusing case, with the same dollar, a mu greater than or equal to due to no in germ order is entirely equivalent to less than or equal to delino for all the range from dollar to dollar.
Got it.
And this is the kind of scenario where the original work on germ order focused, and where we can develop criteria based on comparing the moments of these total outcome distributions.
Okay.
Yeah.
But, the source cautions that finding simple moment-based criteria becomes more challenging when the total outcome distributions do depend on a germ.
Yeah, that's right. The heterogeneity across starting points complicates things.
Yeah, if the rules of the game change,
Right.
depending on where you start, then it gets
That's exactly.
more complicated.
Yeah, it's not enough to just compare the mean or variance of Termway and the Delaney for each dollar to guarantee germ order.
Okay. So given that challenge, the source then presents some sufficient conditions for germ order, specifically for these independently diffusing families.
Yeah.
So let's dive into Theorem 3.2.
Okay, so Theorem 3.2 provides conditions based on comparing transformations of the total offspring generating functions.
Okay.
Specifically Yuki at the view.
Okay.
Part 1 states that if the Caliph moment of the total offspring distribution of Yuki, let's call random variable with this distribution Yuki,
Got it.
is strictly greater than the Caliph moment of Yuki,
Okay.
which we'll call wire. And this Caliph moment of Yuki is finite and greater than 0.
Okay.
Then there exists some delta greater than 0, which might depend on Yuki, such that the expected value of Yuki times the exponential of negative tel times Yuki is greater than or equal to the expected value of Yuki.
Okay.
For all that are ranged from 0 to delta.
Okay.
So this condition relates the moments
Yeah.
and an exponentially weighted moment.
Right. So a difference in the Caliph moment
Gives us this inequality, but only for really small values of dollar.
Yeah, for small values of dollars, or equivalently for 2 near $1 in the original fight function.
Okay.
But this might not give us a uniform delta across all dollars.
Right, okay.
Now, part 2 of the theorem gives us a condition for a uniform delta.
Okay.
And therefore, for the Q greater than or equal to a new Waller in germ order,
Okay.
it says that if the first Kähler moments of U and Waller are equal, so that means the expected value of UE equals the expected value of UO now.
Okay.
For a 1 to thou. And if a specific condition, condition 3.5, holds for some dollar greater than 0, that's the same for all dollars, that's greater than or equal to in germ or in dollar.
Yep.
And condition 3.5 is a comparison involving the Flever-Agel plus 1 moments and an exponential term.
Okay.
So if a dollars is even, we need the expected value of 1 co plus 1y to be greater than or equal to the expected value of 1y times 1y plus mel plus 1 plus double times 1.
Okay.
And if the dollars is odd, we need the expected value of 1k plus 1y times plus del delta times y to be greater than or equal to the expected.